Okay. Then again, a stick was not that expensive. Yes, like on a separate day. Same place, it's like
Yeah, you know what that is.
Pretty close. No, like the data was good when I was getting value, so like I was still getting 705. Yeah, I was trying to have it at one point, I remember that time, and then I ran it again, and now I'm doing everything. Yeah, again, there was one. Yeah. Actually, no, it might not. I'm gonna have to put in some work. Until
all right. I hope everyone had a good long weekend. So thanks for the assignments. If you, is this what you're talking about? Is this who? So I don't want to be responsible for losing pages. So if you didn't staple it, please come get it and fix it. Yeah, you're not. Oh, this one's yours. Sorry. Yeah. Yeah, sorry. I know it sounds like I'm being petty, but I have stacks of assignments from 3 different courses, and I have literally hundreds of pages. I don't want to keep track of loose pages. Okay, so what we've been talking about is we started talking about energy of collections of charges. And so I want to be able to now calculate the energy of eventually some arbitrary continuous distribution of charge. And we're going to build this up the way we build up all of our problems. We're going to start by thinking of individual point charges and building up our charge distribution one at a time by adding these point charges individually. And then you take enough point charges, you can build whatever arbitrary distribution you want. So what is the energy? Oh, let me say assignment 2 I posted on the course website just yesterday. So that should be available. Yes.
It does say it's June the 14th.
Yeah.
But that's Thanksgiving.
Oh, is that another goddamn holiday? God, all we do is take freaking holidays. Okay, I'll change it. Yeah, thanks. If I was in charge, I would just start killing holidays. Thanksgiving, Valentine's Day, Easter, all of those gone.
We don't get from out.
Yeah, well, we still don't need it. All right. So, okay, collection of point charges. what I want to imagine is we do this process, we take one charge and we bring it to some region of space that's completely empty. That costs us no work, right? Work is force times displacement. If there's no electric field and I move a charge, there's no force acting on it and the work is zero. So step one is we move the first charge, Q1, from infinity to its final position. We'll call that R1, measured from wherever our origin is. Okay, so this work is zero because there's no electric fields to basically resist the motion of that charge. And so work one is equal to zero. When we take the second charge, now we're going to bring it to some position somewhere next to Q1. But when I do that, Q1 makes an electric field. And so I have to do work against that electric field. So that costs me energy. Let's assume, just for the sake of argument, that the charges are the same sign. Okay, so step two is we move the second charge, Q2, into position at R2. And so maybe the distance between Q1 and Q2 is, we'll use our script R notation, 1, 2. Okay, so what that might look like, here's Q1 sitting over here, and now Q2 is going to be sitting over here, and this length is R12. Okay, the work, if you were to calculate it, would be 1/4 pi epsilon naught, and then it's going to be Q1 over R12. This is going to be the electric potential due to Q1 at the position of Q2, and then we multiply by Q2, and that gives us our energy. Right, so remember, last time we calculated this for point charges, and we said, well, the work is just equal to the change in potential. If I have Q2 initially out at infinity, where we define the potential to be zero, then its initial potential energy is zero, and I move it next to Q1. This is its final potential energy. Final minus initial is final minus zero. And so that's how much energy it costs us to put that in place. Okay. Well, then we do our third charge and we say, okay, Q3 goes from infinity to R3. So maybe Q3 sits over here. And now what I have to do is I have to do work against the total electric field due to both point charges Q1 and Q2. So this is going to involve things like R13 and R23. And if we were to write down how much work step 3 cost us, it would be 1/4 pi epsilon naught. And then we're going to have the potential at 3 due to Q1. So it's going to be Q1 times the distance between 1 and 3. But that's not the only contribution to the potential, because Q2 is also contributing something, and it's going to depend on the distance between 2 and 3. And then we multiply all that by Q3, that's how much energy it costs. And of course, you can keep doing this process over and over. You bring in a fourth charge, there's going to be 3 terms in here, and then you multiply by Q4, and so on. Okay, so the total amount of energy that it costs us to assemble the entire collection of charges would be, well, it's going to be a 1/4 pi epsilon naught. And there's going to be, well, let's see. There's going to be a Q1 times Q2 contribution divided by R12. And then there's going to be 1 times 3 contribution, Q1 times Q3, R13. Now, if there was like a Q4 and a Q5, we would have Q1 times Q4 over R14 and so on. Ultimately, once we paired up all of the Q1s with all of the other charges, we would move on to Q2. But when we do Q2, we're not going to write this term down again because we've already counted that. So we're going to count 2 with 3, 2 with 4, 2 with 5, and so on. And so it'd be a Q2 times Q3 divided by R23, and there would be more terms to add. All right. So we can express this all a little more nicely using sums. So this is going to be 1 over 4 pi epsilon naught. And let's see. If you just think of the first charge, we're going to sum over the first charge and all other pairs of charges. So we're going to have a sum over I equals 1 to n. And then we need to multiply our Q1 by Q2, Q3, Q4, and so on. So that's all of the charges that, j bigger than I. So if I is equal to 1, I want to include in my sum Q2, Q3, Q4, Q5. Then when I get to I equals 2, I'm not going to do the 1, 2 again. So I'm going to count starting from 3, 4, 5. When I get to Q3, I'm going to count from 4, 5, 6, and so on. Okay. And so it's going to be a product of charges divided by the distance between those charges. All right. This excludes Q2 over Q1 divided by Q2 R21 because it's identical to just switching the indices. All right. Now this is not so convenient because it's kind of awkward, you know, if you have to do a mathematical manipulation of this sum where you're only keeping, you know, the starting point changes depending on which charge you're thinking about. So what you can do instead is you can say, well, why don't I just count all of these twice and then divide by 2 at the end? Okay, so we can instead can intentionally double count pairs of charges and then divide by 2. Okay, so if you did that, you would say the work is, instead of 1 over 4 pi, we'll put 1 over 8 pi epsilon naught. The sum over I is going to be the same. But now your sum over j is still going to have a restriction. What's the restriction going to be? Yeah, it can't equal I, right? So when I move charge 1, it doesn't do work against its own electric field. Same for any value of I. So j cannot be I, but otherwise there's no restrictions. And then it's qi, qj divided by rij. All right. We can rearrange how this is written. So I'm going to pull out the 1/2. I'll have my sum over I is 1 to n. And then I'm going to take my qi over here. I can take the QI out of this sum. I can take anything out of the sum as long as it doesn't have a J index. Okay, it's like pulling a constant out of an integral. So then what's left over? This is the sum of J not equal to I of QJ. Sorry, I want to put in my 1/4 pi epsilon naught. And then we have a QJ over RIJ.
Why can't you have that one of the full on that outside of?
Oh, I could put that wherever I want. I put it in here because I want you to look at this and tell me what it is.
Or no,
It's the potential, yeah. So this is the potential due to all charges except charge I at the position of QI. So this is the potential at the position of QI due to all other charges. Okay, so with that, we could write the work as 1/2. It's the sum of I equals 1 to n. And then we have our QI, and then we have the potential at the position of QI. So this is the energy required to assemble a collection of point charges. All right. If we were to think about a continuous distribution of charge, we would just re-express this as an integral. So for a continuous charge distribution, the sum of QI is going to be replaced with rho d tau, right? So we're going to have some volume of charge, some volume charge density. If I multiply by a small element of volume, that's like the QI at that position, and then we sum over all those little QIs. So if we make that replacement, then W, the work, is 1/2. Instead of the sum of QI, we're going to have the integral of rho, then times V and d tau. So. Now, a question you might ask is, okay, what am I integrating over? So strictly speaking, you're integrating over the charge distribution. But you have some flexibility here because I can extend that integral to any range I want as long as it includes the full distribution of charge, right? We're going to do an example where we'll have a sphere. Okay. Now, if I integrate in a region of space that's outside the sphere, that's fine because rho is equal to 0 there. Okay. So let's just keep that in mind. So we can integrate over the volume where rho is not equal to 0, but we can also extend the integral to all space if we want to, if desired, since rho will equal 0 outside the charge distribution. All right. I want to do one more thing before we do an example, and so we can express this in different quantities. So if you remember, like it was a week ago, I guess, but our last class, we had this plot that said like if you know the charge density, this is how you can find the electric field and the potential. Or if you know V, you can find the electric field and potential in this way. And so there's this map, how we could go between all these important quantities in electrostatics. And so what I'd like to do is see if we can come up with an expression in terms of the electric field. So we next attempt to re-express this work or the energy in terms of the electric field. All right. So we have Gauss's law. In differential form, said the divergence of E is equal to rho over epsilon naught. So we have charge density in our expression, so we could write that as epsilon naught times the divergence of E. So rho is epsilon naught divergence of E. Okay. Well, let's put that in. So the work is going to be 1/2. I'll pull out the epsilon naught. So we have epsilon naught over 2. And so instead of rho, we're going to have the divergence of E. And then we still have the potential. And now we have the d tau. All right. What could we do with this? We have like the integral of a derivative times another function. What does that naturally lead you to? Integration by parts. Okay, but it's not it's the integration by parts for divergence. But it always works the same way. So let's integrate by parts. Okay, so this is going to be equal to the epsilon over 2 is going to stay the same. If you think of regular integration by parts, that's like the integral of f times the derivative of g, right? How do you do that? Well, first you take f times g and you evaluate it at the boundaries. Well, okay, so let's do the same thing. We would do E times V. But what's the boundary of a volume? It's a surface, so it's going to be a surface integral. So, right, you don't always have to look these things up. You can just figure them out. All right, so that's the boundary term. And then integration by parts has a minus. So if it's the integral of f times the derivative of g, it would be minus the integral of, I guess, f g times the derivative of f or something like that. So we're going to do the same thing. Now we're going to have our volume integral again. But instead of the derivative acting on E, it's going to act on V. So we're going to have an E. Now, how does, like I can't take the divergence of a scalar, so what do I do instead? Take the gradient, right? So dot rad V. Okay. But what is the gradient of V? It's E, it's not exactly E, it is negative E. That's right. Okay. So what we have then is that our work is epsilon naught over 2 times the surface integral of V times E dot dA minus, well, in fact, it's not going to be minus because you have minus and minus, so it's going to be plus. E dot E is just E squared, so it's plus the integral of E squared tau. All right, so this is a surface integral, this is a volume integral. Okay, now the reason that I emphasize that we could extend this integral to all space is so that we could take advantage of that here. What's going to happen to this boundary term if we let's imagine that our volume now is a sphere with a radius that goes to infinity. What's this integral gonna become? Well, it'll have infinite area, but let's think about what are these functions inside here? What are they equal to? At infinity. 0. That's how everything we derived up to this point relies on the potential of a point charge. Now, the potential of a point charge, we chose to make that 0 an infinite distance away from the point charge. So if we extend our volume integral to all space, our surface goes out to infinity, but out there, the potential is 0. In fact, your electric field would also be 0, infinitely far away from your charge distribution. So that's what we want to do. So as above, we can select a volume that, I don't know, covers all space. Therefore, our surface is out at infinity, where V is equal to 0, and well, in fact, E is going to be 0 as well. And so therefore, what we can say is that our work is equal to epsilon naught over 2 integral of E squared d tau if we integrate over all space. Sorry, yeah, and it's not a vector. You are exactly right. Thank you. Good. All right. So let's do an example. So example, let's find the energy of a uniformly charged spherical shell of radius r. All right, now we have two approaches that we could take to solve this problem. We could use the expression here in the red box. In that case, we would have to work out the electric field due to this uniformly charged spherical shell. What we would find by Gauss's law is if all the charge is on the surface of the shell, then inside there's no Q enclosed, so the electric field would be 0 inside, and then outside it would look like a point charge. So you could write down the electric field of a point charge, square it, integrate all space, starting from where E is not 0, so starting from R is capital R out to infinity. What I'm going to do is, just for fun, I'm going to use this expression, except we don't have a volume of charge, we have charge smeared out over a surface. So instead of a rho d tau, we're going to have a sigma dA. Okay. So let's start with, so work is going to be equal to 1/2 the integral of sigma times V times dA for a, I don't know, surface distribution of charge. So at the surface, what would the potential of a sphere be at its surface? What does it look like if you're sitting at the surface? It looks like a point charge, right? So what would the potential of the point charge be? Yeah, that's right. So what did I uniformly charge? So okay, I'll use Q. So this is the charge of sphere. Okay. Well, sigma is going to be the total charge divided by 4 pi r squared. Okay, and so dA, if we're integrating over our surface, we're integrating over a sphere, we're doing spherical coordinates. What should I use for dA?
Our percent data D.
That's right. Okay, good. In fact, I mean, I think what we'll see is that we don't actually need to use this, but let's write it down anyways. All right. And we'll see why we don't need to actually explicitly write that down. So the work is going to be 1/2 the integral of sigma. Sigma is Q over 4 pi r squared. Let's see, then we have the potential 1 over 4 pi epsilon naught Q over R. Okay, so then we have our dA. All right. What's interesting about, or what's actually nice about this problem is that we have only constants inside our integral. We're integrating over these angles, but there's no angle dependence anywhere here because everything has spherical symmetry. So this is equal to 1/2 Q 4 pi r squared 1 over 4 pi epsilon naught Q over R, the integral of dA, and that's just 4 pi squared. And so cancel, cancel. And what we're left with is just 1 over 8 pi epsilon naught Q squared over R. So this is equal to 1 over 8 pi epsilon naught Q squared over R. All right, good. Now, what should be possible is we should be able to use the other forms and the one involving the electric field, and you have to get the same answer. So that would be a useful thing to try. All right. Any questions about anything? All right. So we are now into our last section of chapter 2. And it's about conductors. And you've probably seen a lot of this before. Maybe there's one thing that we kind of need that we haven't talked about previously in another course. So as you know, in a conductor, you have these, all materials are made of atoms. In some materials, all of the electrons are tied tightly to their host atom. Those are insulators. Those don't have any mobile charge that can easily move around. In conductors, some of the valence electrons in the outside shell can detach from their host atom, and then they can move throughout the material. So they have no they have no fixed home. They're free to flow around. So in a conductor, some electrons in the valence shell of atoms leave their host and can move freely throughout the material. Okay, so what we're going to do is we're going to try to work out a bunch of properties of conductors in electric fields. And it's going to turn out to be not so difficult because we've done a lot of the work already. So 1, when we place a conductor in an external electric field, Well, let's just imagine what's gonna happen. So I'm gonna draw a picture as we write this down. So this is our conductor. Somewhat spherical, just so it's easy to draw. And then I'm gonna imagine that we're gonna have an electric field. Maybe before the conductor was put in place, the electric field was uniform. Okay, I'll extend some of these lines a little bit more in a second. So, well, what's going to happen if I wanted to produce this kind of electric field, somewhere I'm going to have some positive charge distribution on this side and maybe a negative distribution on this side, right? So like electric fields point away from positive charges and then they point towards negative charges. So however I make this electric field, there's going to be like charges piled up somewhere. Well, this conductor has electrons that are free to roam around, and they're going to be attracted to the positive charge, or if you like, they're going to be attracted to the electric, if you put a charge in an electric field, a negative charge, it goes in the opposite direction of the field. So they tend to migrate this way. So you end up with a migration of electrons towards the left edge of this conductor. Now, it's only the electrons that can move around, but if I take a bunch of electrons and move them to the left, that leaves behind an excess positive charge due to the ions of these atoms that sits on the right. So initially, when I first place my conductor in this electric field, there is an external field that passes through my conductor. And that external field drives this migration of charge. But when my charge migrates, it makes its own electric field, right? And it points from positive towards negative. And so we're going to have some kind of internal electric field. And this migration of charge is going to keep happening until this internal electric field exactly cancels the external one. And when that happens, you end up with your net electric field inside your conductor is 0. Okay. So all right, so the external field drives the migration of charge in the conductor. Eventually, the internal field, due to the rearrangement of charge, completely cancels the external field. Now, I said eventually as if this takes some time. I mean, it does take some time, but it's almost instantaneous. Okay, so you end up with no electric field inside your conductor. So that's our first result. E equals 0 inside conductors. All right. Well, the second property is from Gauss's law, from the differential form of Gauss's law. So if we know that E equals 0, then by Gauss's law, which we've already used today, the divergence of E is equal to rho over epsilon naught. If E is equal to 0, the charge density is equal to 0. The charge density rho is equal to 0. So that means we have to be maybe a little bit careful. It doesn't mean that there's no charge in a conductor. What it means is that there's equal negative and positive charge, and that distribution is uniform inside the center of the conductor. So there's no net charge density. Well, I mean, I can put charge on a conductor. So if I charge a conductor, where does that charge have to sit? It has to sit at the surface. Okay, so any non-zero net charge on a conductor must reside on a conductor surface, on a surface. I said a surface instead of the surface because you can have conductors that have cavities. And in that case, it's going to have an outside surface and an inside surface, and you can have charge on either one or both of those. Okay. So the third property is it's going to be about the potential of a conductor. So we know that the change in potential is equal to minus the integral from some starting point A to some ending point B, E dot dl. Okay, so here's our conductor. Here's the electric field that has to be 0. And here's some point A. And here's some other point B. There's nothing special about these points. And here's some path that connects A to B. There's nothing special about that path either. Well, if I just look at this integral, E is 0 everywhere on this path. And so this integral is going to evaluate to 0. So therefore, delta V is the final potential minus the initial potential. It's going to have to be 0 because E is equal to 0. In other words, V at A and V at B are equal. And I could have chosen any points for A and B inside my conductor, and I'd always get that result. So the potential on the conductor is everywhere the same. It's constant. People sometimes make the mistake that a conductor has 0 potential. That's not true. It's not 0. It doesn't have to be 0. It's just constant. Okay. I could have also taken points on the surface of the conductor, and I would have got the same result. So the interior and the surface are all at the same potential. So the entire conductor is at a constant potential. All right, so that's 3 properties. E is 0, the potential is constant, and any excess charge sits on the surface. And there's one more that we're going to do. Okay. So this will be property 4, I think. I'll just tell you what the property is, and then we'll go through a little argument. E outside the conductor. Well, I don't like how I said that. E is obviously 0 inside, and so E is perpendicular to conductor surface. Maybe I'll just leave it at that. Okay, and so let me draw. Here's the surface of a conductor. So in here, this is our conductor. And this is where E is equal to 0. And out here is like some kind of free space. So E doesn't have to be 0 out here. So let's just imagine that we had a situation where the electric field was not perpendicular to the surface. Well, in that case, what I could do is I could say, all right, let me separate this into components. One that is parallel to my surface and another that is perpendicular. And let's now also imagine that our conductor is charged. Okay, so it's charged, and that charge is going to have to sit at the surface. And so I'll put some positive charges here sitting right close to the surface. So this is a charged conductor in an external electric field. Well, if that was the case, then this parallel component of the electric field is going to exert a force on this positive charge at the surface, and we're going to start getting charge flowing perpendicular to our surface. So if this situation was situation with, say, E parallel not zero was allowed, it would exert a force on the charges at the surface, and we would get a flow of charge along the conductor surface. So if you remember, what we said we were going to restrict ourselves to initially anyways was electrostatics. And what we meant by electrostatics was that all of our source charges are going to be stationary. And so this flow of charge in our conductor violates one of our assumptions of electrostatics. And so if we're dealing only in electrostatics, then only the perpendicular component of the electric field can survive. And that means electric fields intersect conductors perpendicularly. Okay. This violates the assumption of electrostatics. And so therefore, electric field, maybe I should say external electric fields intersect conductors perpendicular to their surface. All right.
Then if we maybe take this beyond an electrostatics assumption, is that?
Yeah, so you could maybe have more complicated figures. Yeah, and so that would, my guess is that that's going to be reserved for like 401. Yeah. All right. So those are the major properties of conductors and electric fields. And so now I want to think about some examples and potentially uncover some useful features of this. And we have like 30 minutes left, so that's pretty good. So let's do conductors with cavities. All right, so let's imagine for this example, let's take a neutral conductor, a neutral spherical conductor with a cavity of arbitrary shape and position. So I'm not going to limit myself to a cavity that's in the center and it's also spherical. Doesn't have to be that way. So what we'll do is we'll start with our spherical conductor and then we'll draw our cavity something like this. And so here is our cavity. All right. What we're going to do is we're going to place a charge Q inside our cavity. And again, I'm not going to restrict myself to where Q sits. It can be anywhere in that cavity. So let's put a point charge Q inside the cavity at an arbitrary position as long as it's in the cavity.
So if this were a sphere, would the cavity just be a hole all the way through, or like a thing?
No. So like if you were sitting inside the cavity, you could look all around you, you'd see conductor walls.
Oh,
Yeah.
yeah, balls.
That's right. Yeah, that's right. So I mean, I can't draw
Yeah.
a 3D cavity. You'd only see the thing. Yeah. So yeah, that's a good question. It's not all the way through. Okay. Well, what's going to happen? So here's Q. We'll assume it's positive just so we have something to talk about. All right. Well, I know that no matter what, I'm going to have 0 electric field inside the conductor. Now, obviously, this point charge makes an electric field inside the cavity. And so the point charge is going to, I'll draw some representative lines. As we just learned, these lines would have to intersect the cavity wall perpendicularly. So try to be somewhat consistent with that. All right, so how is it possible that I have an electric field in the cavity and then it abruptly stops once I get to the conductor wall? How does that work?
The surface of the cavity to the line.
Yeah, that's right. So if Q was positive, we're going to get a migration of charge that's going to surround that cavity, and that migration is going to continue until the electric field inside the conductor is 0. So if you like what you could think of, if we could somehow go from a situation where we at one moment had an empty cavity and then instantaneously we place a charge in there, then initially that charge would make an electric field that goes through the conductor. Those electric fields are going to exert forces on the charges in the conductor, causing them to move until we achieve E equals 0 in the conductor. All right. Now, if the conductor is neutral, what happens when we get negative charges collecting around the cavity?
There'll have to be some compensation.
Yeah, there'll have to be some positive charge. Where's that going to sit? Outer surface. Okay, so that's right. So we get let's say electrons from the conductor migrate to the cavity surface and cancel its electric field inside the bulk of the conductor. What I'm trying to say by bulk of conductor is the electric field that's actually in the cavity is not 0. It's only when you're actually in the solid material of the conductor where E is 0. All right, so this migration leaves behind excess positive charge on the outer surface. So the question that I have is, how does that positive charge distribute itself? Are we gonna have more positive charge at the outer surface, like closer to the cavity or farther away, or what? So what would determine how a collection of charge distributes itself? Like what causes charges to move?
The electric field produced by Q inside the cavity.
Yeah, so it's so you're right, electric fields determine how charges distribute themselves. Do the charges on the outside surface know about Q in the cavity? No, the electric field's zero there. So, okay, so this little Q can't determine how the charges on the outside surface distribute themselves, so what does determine that?
The surface charges and distributed.
Yeah, they're repelling one another, right? And so, if I have one surface charge here, all it feels is the other surface charges that are nearby. And so, because the electric field is equal to 0 inside the conductor, the distribution of I don't know, charge at the outer surface is determined by, let's say, the Coulomb repulsion of those charges. And so that means they're just going to distribute uniformly. And so, i.e., the outer surface charge is distributed uniformly. I don't know, for me, that's kind of like it's a kind of a neat result. It's a bit unintuitive, actually. You would naively think that if I have a bunch of negative charge around the cavity, that's going to attract more positive charge nearby, but that's not the case, okay? And it's this effect of the electric field being canceled that allows this. All right, so there's another kind of neat thing here. Those surface charges on the outer surface don't feel the presence of the charge in the cavity, but they communicate the fact that it's there because there's going to be now an electric field that sits outside of this neutral conductor. So we can use the integral form of Gauss's law to find E outside the conductor. You may already know what the answer is going to be. It's going to look like a point charge. But let's go through the exercise. Anyways, so I'm going to pick a Gaussian surface that surrounds a spherical Gaussian surface that surrounds my conducting cavity, and we'll make that some radius r. Okay, so Gauss's law, integral form is Q enclosed over epsilon naught is equal to the surface integral of E dot dA. So this kind of, we're using Gauss's law a lot. today. We've used the differential form twice and we've used the integral form, now we're using it once. All right, let's start with Q enclosed. So Q enclosed, we're just gonna add up all of the charges that are inside this dashed purple line. There's a positive charge on the outer surface, a negative charge on the inner surface, and a point charge in the cavity. And so if we add all of those up, we get Q outer plus Q inner plus Q. So these are the surface charges. They will cancel, yeah. So we said we were going to start with a neutral conductor, and so that means any negative charge that migrated to the inner surface of the cavity left behind an equal amount of outer charge on the external surface. And so Q outer is equal and opposite to Q, maybe, yeah, minus Q inner. So if Q inner is negative, then Q outer is positive. And so therefore, Q outer plus Q inner is equal to 0. And so our Q enclosed is just Q, the point charge. Now, if I evaluate this integral, E dot dA, well, the electric field has to be outside of our, let's imagine I made my Gaussian surface like really close to the outside surface of this spherical shell. One of our rules for conductors is that the electric field has to be perpendicular to the surface. And so that means E must be radial. And dA for a spherical surface is also radial. And so this just becomes E dA. If the outer surface charge is uniformly distributed, then the electric field would be constant everywhere at every point on my Gaussian surface. And so if it's a constant, it comes outside. And dA is just the integral of dA is just the area of my Gaussian surface. And so that's going to be E 4 pi r squared. And so it must be then that E, well, okay, let's just do this. E 4 pi r squared is Q enclosed, which is just Q over epsilon naught. And that leads to E is 1 over 4 pi epsilon naught Q over r squared. And we can even say that it has to be radial. And so we have this funny situation where we have a point charge inside the cavity of a conductor. The cavity has a weird position and shape, and the point charge is at some weird position, yet the electric field that we see outside the conductor looks as if we have a single point charge right at the center. Yeah.
Is there a reason to not, like, I know we said one of our axioms is that there's no electric field inside of the conductor.
Yeah.
But why, as we did before, where you said that when you put the conductor in an electric field, it generates an electric field inside of the conductor.
Yeah, momentarily.
Yeah, why,
Yeah.
why would we assume the same thing here, where it's like the electric field created by the point charge in the cavity does create an electric field inside that conductor, but the conductor arranged itself to create an electric field opposite of that, so that the net electric field is 0 inside of it. But
Yeah.
it continues outside of it. It's like,
Yeah, that's the same thing, right? Yeah, yeah. So like that is what would happen if I instantaneously somehow could put a charge, like at an instant, I put it in the cavity. There will be an electric field in that conductor. There will be a response, and so the net, like you said, the net electric field will be 0 in that conductor, but the point charge. Like, in fact, it doesn't just continue as if the conductor wasn't there, because if we did that, So if I had my cavity here and Q was here, then the electric field due to that point charge, if it just continued ignoring the conductor, yeah, that's no longer radial. So that's not what happens. So I think we have to be a little bit careful about understanding that what's happening is you get a migration of charge around the cavity to cancel that electric field of little q. That leaves behind excess positive charge on the outer surface, and it's that excess positive charge at the outer surface that creates the radial electric field. Yeah, but that's a nice clarification question. All right, so let's just make this final point. So let's say outside the conductor, it looks as if we have a single point charge Q at the conductor center. All right. So we have only one more topic to do, and it's kind of a neat one, actually. So what we're going to try to do is we're going to try to imagine the electrostatic pressure that a charged object experiences. And if you think about it, like there must be something like that, because let's just take a spherical shell and we'll put a charge on that shell. Like those charges, they feel a Coulomb repulsion from one another. And so if there was nothing holding them in place, they would just spread out and they'd go off to infinity. So there must be some constant force that's pushing them out, and there has to be something holding them there. But that electrostatic force we could express as a force per unit area on the surface and then find some pressure. And so that's what I want to try to do. Okay, so this is 2.5.3. This is surface charge and electrostatic pressure. All right. So what we're going to have is, here's our conductor, and E is going to be 0 inside that conductor. Here is our free space. I imagine that we have some charge density sigma on the surface of our conductor. So we have a conductor with surface charge density sigma. All right. So let's just remember a few things. We had boundary conditions that we developed, and what we said is that E perpendicular above a surface charge density minus E perpendicular below a surface charge density had to be equal to sigma over epsilon naught. We also had one that said that E parallel above is equal to E parallel below, but this is the one that I want to use today. Well, what is the electric field below this charged surface? 0. Okay, so this has to be 0 because there is no electric field inside our conductor. All right, and so one thing we could say for sure is that the electric field above is perpendicular and it's equal to sigma over epsilon naught. So I could draw that in my picture here. I could take like a little patch. Here's a patch of some area. This is a patch of area sigma and sorry, what am I doing? Of area A and charge sigma times A. Okay, and we just worked out that the electric field at that position is just sigma over epsilon naught. Maybe I could draw, say E is equal to sigma over epsilon naught. So that already kind of shows you that, well, I have some patch that's charged and it's in an electric field, so there must be a force on that patch. But we have to be a little careful because that patch is partially responsible for contributing that electric field. And a charge does not experience a force from its own electric field. So if I want to find the force on this patch, I have to find the electric field due to all other charges except for that patch of area A. Okay, and so that's what we're going to try to do. Okay, so what is the force on a patch of area on the conductor due to this electric field? All right, well, force on the patch is due to E from all other charge except for Q patch, which is equal to sigma A. All right. So let's imagine that you cut out that little piece of patch. What's the electric field going to look like in that case? Well, if I just had an isolated patch, it would make an E patch above and an E patch below. We did this calculation for charged surfaces in the last tutorial you worked out, or maybe you're going to work out capacitor stuff tomorrow. So if you have a charged surface, the electric field above is pointing up and the electric field below is pointing down. So at the location of the patch, what are we going to have? Above it, we're going to have the net electric field above is going to be equal to the electric field due to all other charges, right? So this is from all other charges. Plus whatever the patch is contributing itself. Okay, so if the patch wasn't there, this would go away. And then below, we're going to have E below is going to be, yeah, so it's not zero. If I had the whole conductor, the electric field would be zero, but I'm imagining just this little charged piece of patch. So below it, we're going to have whatever would be there without the patch in place, and then minus E patch, because below we're pointing downwards. So if I was to add these two together, then, so whoever said zero is right. Like we're eventually going to say that the net electric field below the patch has to vanish. But let's average these two. So if I take 1/2 of the electric field above plus the electric field below, that's going to be equal just to the other. Because the patch contribution just cancels. Okay, so the magnitude of E other is equal to 1/2 E above. Let's go look at our picture. E above is the sigma over epsilon naught. And then E below is 0, as someone said. So that's exactly right. So this is going to be sigma over epsilon naught plus 0, which is equal to sigma over 2 epsilon naught. Okay, so it's kind of a cute result actually, because what it tells you is that the total electric field just above the patch is 50% due to the patch itself and 50% due to all the other charges. And that's not obvious. At least it's not obvious to me. Nevertheless, that seems to be the case. Okay, so then the force on our patch. Let's just work out the magnitude of the force on the patch. So force on our patch of area A is equal to, well, it's equal to the strength of the electric field due to all the other charge times the charge of the patch. But we've already worked out both those things. E other was sigma over 2 epsilon naught. Q patch was sigma times the area of the patch. And so this is equal to sigma squared over 2 epsilon naught times A. And so this electrostatic pressure is force per unit area is sigma squared over 2 epsilon naught. All right, let me just write this in one other way. I'll write it in a funny way. I'm going to write this as 1/2 epsilon naught. So this 1/2 is this 1 over 2 here. I stuck an epsilon naught in the numerator, so I have to add another one to the denominator. So I could write this as sigma over epsilon naught squared. But sigma over epsilon naught is just the total electric field. And so this is E, the total electric fields. And so we get that the pressure is equal to, we could express it as sigma squared over 2 epsilon naught, or 1/2 epsilon naught times E squared. And so it's an outward pressure because we have a positive charge creating an outward electric field. Force would be pulling them out. If you had negative charges, you'd have an inward electric field, but the force on the negative charge would still be out. So whether you have positive or negative, this is always an outward pressure for your charge surfaces. Okay, good. So that's chapter 2 wrapped up. We will start chapter 3 next week. And I think chapter 3 is working with the potential and doing things like solving Poisson's equation and stuff like that. Okay. So we'll probably end up solving some differential equations, maybe do some separation of variables, all that good stuff. All right, good. Thank you very much.